So we've been talking about colligative properties of non-electrolytes. Now we're going to look at the electrolyte solutions. Strong electrolytes affect the freezing point and boiling point more because they separate into ions. So there are more particles, right? The Van Hoff factor is the ratio of moles of particles to the moles of formula units dissolved. And it's given the symbol I. I have no idea why. Moles of particles in the solution divided by moles of formula units dissolved. Now you would expect that for something like sodium chloride, that it would be 2 moles of particles for every 1 mole of formula units. But they're not actually the same because some ions effectively pair up in solution. And that's why we have this Van Hoff factor. So here are some actual Van Hoff factors, measured ones and expected. So for a non-electrolyte, you don't have any ions forming. You expect 1 and you get 1. For sodium chloride, you would expect to have a Van Hoff factor of 2. You would expect 2 ions for every mole of formula units. It's actually only 1.9. So the measured Van Hoff factor is generally a little bit less than what we expect. For magnesium sulfate, we expect 2, we get 1.3, etc. Ion pairing is you've got these ions that are solvated. They're surrounded by water molecules with the ion dipole forces. But these two are still going to kind of hang out together, and so they act like one particle, even though it's 2 ions. So we have to make a correction in the equations for electrolyte solutions. And the equations are the same with the addition of this Van Hoff factor. So that multiplies the molality and the constants. So calculate the freezing point of an aqueous 0.1 molal iron 3 chloride solution using a Van Hoff factor of 3.2. So this is an example where an actual Van Hoff factor is given. If you're not given the Van Hoff factor or a place to go look it up, then you should just use the expected one based on the number of ions. So if we have FeCl3, what would the expected Van Hoff factor be? 4. Because when this forms ions, you get 1 Fe3 plus ion and 3 chloride ions, total of 4 ions. But we're told here that the factor's 3.2. So we have molality is 0.1 molal, and I is 3.2, and we need the freezing point depression constant for water, which is 1.86 times degrees Celsius per molal. I just happen to remember that. So the change in the freezing point equals I m times Kf. The balances are mooing at us. So the Van Hoff factor of 3.2 times the molality of 0.1 molal times the 1.86 degrees Celsius per molal. Molals again cancel out. 3.2 times 0.1 times 1.86. So the change is 0.5952 degrees Celsius. What's the freezing point? Is water, yeah. So pure water would be 0. And the change, freezing point goes down. It's always expressed as a positive number. I disagree with that, but we have to deal with it. The freezing point goes down, so we subtract this from the normal freezing point. So the freezing point would be negative 0.5952 degrees Celsius, or negative 0.60. Because it started at 0 and it went down 0.5952. Any questions? Strong electrolytes also have a larger effect on vapor pressure lowering because, again, you've got more particles. So calculating vapor pressure for strong electrolyte solutions, we have to account for the dissociation of the solute when we're calculating the mole fraction. Solution contains 0.115 moles of water and an unknown number of moles of sodium chloride. The vapor pressure of the solution at 30 degrees Celsius is 25.7 torr. The vapor pressure of pure water at 30 degrees Celsius is 31.8 torr. Calculate the number of moles of sodium chloride in the solution. Well, the vapor pressure, so the vapor pressure of the solution is equal to the mole fraction of the solvent, water, times the vapor pressure of pure water, or pure solvent. So this one is kind of backwards from other ones that we've done. Here we're given the vapor pressure of the solution and the vapor pressure of the pure water, and we're not given enough information to find the mole fraction. But we can calculate the mole fraction from these pressures. So the mole fraction of water is equal to the vapor pressure of the solution divided by the vapor pressure of pure water. The vapor pressure of the solution is 25.7 torr. Vapor pressure of pure water is 31.8 torr. Torr cancel out. .80817 would be the mole fraction. We're trying to find moles of sodium chloride. This is the mole fraction of water. What's the mole fraction of sodium chloride? 1 minus that, right? Is that really the mole fraction of sodium chloride, or is that the mole fraction of particles? Because sodium chloride separates into ions, right? So that other mole fraction is the fraction of ions, not sodium chloride formula units. So we shouldn't write that here. It's ions. It's the number of pieces, the particles. So that's our mole fraction of ions. So that's going to equal moles of ions divided by moles of ions plus moles of water. Right, because that's the definition of a mole fraction. So we've got moles of water. Let's say that let X equal moles of ions, because it's too much writing. So we've got X divided by X plus this 0.115. And that's equal to 0.19183. So we're going to have to do some algebra here. If we cross multiply, we're going to have this x plus 0.115 times the 0.19183. And we would have to distribute this through here. So we're going to end up with 0.19183x plus 0.19183 times 0.115. So then we have to get all the x terms on one side. Right, so this is 1x, and I'm going to subtract this. I'm going to move, I'll just change colors so that we don't get lost. So I've got x minus 0.19183 times x is going to be equal to 0.02206. So this 1 minus this comes out to be 0.80817 times x is equal to 0.02206. Divide both sides. X equals 0.02796 moles of ions. I'm being a little sloppy with the sig figs there. How many moles of sodium chloride is that? Divide by 2. Because sodium chloride forms 2 ions. So we have 2 moles of ions is equal to 1 mole of sodium chloride. Now that is, you could use the Van 't Hoff factor here. That is the expected. Since we're not given a value, I'm just going to use the expected factor, 2 to 1. I just really don't have space. Go down to this corner now. So that's moles of ions. So I've got 1 mole of sodium chloride for every 2 moles of ions. So I take that value and I divide by 2, and 0.0136 moles of sodium chloride. Any questions? These problems like this are kind of challenging. They definitely involve problem solving. It's not just, oh, I can plug it into this equation and be done. Colligative properties, like I mentioned earlier, are important in medical settings. The osmotic pressure of a solution that's administered to a patient is critical. So you go to the hospital and they stick a needle in your arm and give you an IV fluids, right? So the osmotic pressure of that fluid that they're putting into your veins needs to match the osmotic pressure of your blood. Because this is what happens if it doesn't. So this is your normal red blood cells. And if you have a fluid here that is isoosmotic to your blood plasma, the cells are fine. This has an equal molality of particles to what's inside the cells, and so it doesn't cause osmosis either way. This is what happens if you have a hyperosmotic solution. So the solution outside is more concentrated. That's going to pull water out of your cells, and that doesn't look like a good situation. That's called crenation, and it causes them to shrivel up and get all spiky. Hypoosmotic isn't good either, though, because here we have not enough solute, and that will cause the cells to absorb water, and they can actually burst. So you don't want that happening in your body. Bursting blood cells is only good if you've got like stains on clothing, like cut your arm and you bleed all over your pants or something. If you soak that in cold water, just leave it there. In cold water, the cells will eventually burst, and then it's much easier to wash them away. Don't get into hot water with that. Any questions about this? So I kind of already went over that. Hypotonic, isotonic, hypertonic are other words that they use for hypoosmotic. So isotonic or isoosmotic saline is 0.9 grams of sodium chloride per 100 mils of solution. That's a 0.9% mass to volume, and that is okay to be pumping into your veins. That's not going to cause osmosis in any direction. Common units used in medicine are mass to volume percent, because they want to know, okay, what mass of medication are we giving this person? But the easiest thing to measure is volume. So you can measure it with a syringe or in a bag of IV fluid or whatever. So they use mass to volume percent a lot. That's the end of that section.